There we go. Yeah.
Did you buy that just for us?
Hey, it works. Now my ears hurt. I will begin with a word of prayer. I'll do it again if I have to. Okay. Dearly Father, we thank you for this day. I thank you for these students. And I just pray that you guide our work today. Help us to glorify you in what we do and to learn a little bit more about your creation, Lord. In your name I pray. Amen. Now, I got that whistle for coaching basketball like last year. And I should never coach basketball. It's really, really, really bad. Like, bad. As in, like, we never won a game. I taught them no skills. I'm really the worst coach possible. Anyway, so this is lecture 10, I think, and I've got a couple examples here sort of on the same topics as we did last time, so let's start with those. So suppose you purchase a car, right, for $24,850, including taxes and fees. If you finance that amount for 4 years at an annual interest of 8%, all right, then what? Find the monthly payment, and what else? Oh man. Oh no. I brought the wrong notes.
Oh no.
Well, I hope you guys know the formula. So what's the monthly payment formula? Do you guys remember? Well, somebody better remember, otherwise we're just going to sit here all day.
Is it A equals P?
We need the PMT formula.
PMT is equal to A times R over N over 1 minus 1 plus R over N.
Thanks. Let me steal your... I thought I had the book with me, and I picked up the wrong chapter. This is the danger of cutting pages out of a book, you know? So we get R over N divided by 1 minus parentheses 1 plus R over N to the minus NT. All right? And thank you. Thank you. Okay, so then the question then is, for this one, what is the... Let's see here. What is N? Number of payments. Is it the number of payments per year, or? So for us, it's how many here? 4? I think it's 12, right? So we're assuming monthly payments, because it says monthly payment, right? So N equals to 12. Now, I think you're right that the T is equal to 4 years, sure, right? That's true. The rate, 0.08, right? And I think that's all we need. So here we go. We do $24,850 times 0.08 divided by 12 divided by 1 minus parentheses 1 plus 0.08 divided by 12, close parentheses, to the minus NT. Let's see, N times T is what? 4 times 12, right?
48.
48. So that's 48 total payments, minus 48 there. All right. And now we just got to crunch those numbers. So I could, think I'll use my, I hope everyone's top-hatted. You had plenty of time. I'm finishing it now. So I will, for kicks, let you top hat again. Let's see here. Here you go. Next top hat code. Come on. 6391. Hope you remember that, because I'm going to another website here. So you might want to write that down. I'm about to switch windows here.
Do we have to do that if we've already put the other one in?
I don't know.
Yeah, you do.
Yes.
I mean, you don't have to. I can't force you. Let's see, you're 2.4. But it would be good if you did. 850 times 0. I mean, you paid a lot of money for that top ad. Don't you want to get more use out of it? No? 1 minus. I think I got it. Oh, I think I'm, what? Oh, wait a minute. Sometimes Wolfram Alpha is too smart for itself. I know it looks funny, but that's right. So I think the payment, 600, and for me it's $606.66. All right. Let me just double check my, I got the answer over here so I can check it, I think. Yep, okay, that's good. And then how do we, so then here's, this is something we haven't done yet. So that's, we more or less did this problem last time, right? But we didn't answer part B. What's the total amount of interest paid over the loan? How would you figure that out? Let's think through that. So think of it in these terms. To figure out, sorry, I need to flip back to my, there we go. So to figure out the, come on, you can do it. You can do it. You can do it. Do it. Ha, okay. Hey. I duct taped it last time. Come on, duct tape. I'm not kidding. I've got duct tape right here. Dr. Putney told me duct tape it. Apparently the math department got these on a deal from IT, who was retiring them after years of service. I'm not sure what deal we got exactly. Let's see here. Come on. And
Oh no!
oh, really? Well, it's going to be hard to keep shaking it while lecturing. That's no. Oh, I turned it off. There we go. There we go. So think about this. The total amount of interest paid. So all you need to do is figure out. Think about it this way. You get a loan to pay for a $24,850 car, right? And then how much money do you pay for the loan? Well, you just take the total number of monthly payments times the monthly payment, right? So that the total amount of money that you pay is going to be what? It's going to be the amount that they pay. It's going to be interest plus that cost, right? So all we need to do is to take the total, the monthly payment, right? PMT times how many payments are there? Total 4 years, right? So 48 payments. This is equal to total amount paid, right? And so what's that? We take the what? The 606.66 times what? Times 48, right? 606.66 times 48, we get $29,119.68. $119.68. All right? So if you paid that much, how much interest did you pay? Well, we have to subtract the interest paid will be that total cost, right? 29,11968 minus the purchase cost, 24,850. That difference will be the interest, right? And so let's see here, minus 2485. Oops, come on. So I get $4,269.68. 4269.68. So there you go. That's the interest paid. To calculate interest paid, what you need to do is calculate the total amount of monthly payments that you paid, right? And then subtract the amount that you got loaned to start with, all right? Does that make sense? Oh. So that doesn't seem too, that doesn't seem too bad for a car, does it? In some sense, like, if you wanted to buy the car without getting a loan, if you would without financing, right? You do what? If you could just give them, if you've got $24,850 just sitting in your pocket, you can just buy the car outright, right? If you do that, how much money have you saved? You've saved yourself what? $4,269.68. Although I wonder if that logic really makes sense in the current economy with 9% interest. You know? Because I don't know. As the loan, if you think about it, with inflation, right? As the years go on, the money you're paying back your loan with is worth less, right? So the monthly payment in the fourth year, you're affected. But then again, all things considered, unless your salary also goes up with inflation, that logic kind of doesn't help, does it? So it's a nuanced question, you know. But I think as a generic point of order, if we listen to Dave Ramsey and people like that, right, we should always buy cars, what? With money in our pocket, not on a loan, right? Pretty much. But of course, especially at your time in life, you don't have that kind of money sitting around, right? So a lot of you are just kind of like, we have to get a loan. I mean, I think I was like that. You like, speak for yourself. I've got investments, right? I mean, some of you do. Let's see here. Example 2. After making payments of $895.10 for 8 years on a 30-year loan, all right, at 8.5% interest, you decide to sell your home. What's the loan payoff? What's that mean, loan payoff? What that means is when you sell the house, right, you don't transfer the mortgage to the next person. That's not how it works, right? Once you sell your house, you close out that mortgage. So that means that you have to pay the rest of the principal at that time when you sell your house, right? So it's kind of like what I was talking about last class with paying ahead on the loan. It's just you pay ahead everything that 1 month, all right, when you sell your house. And this is how much money you would need to pay off the rest of the principal in this situation. Actually, I don't think they even tell us. They don't even tell us what? They don't even tell us how much the loan was for, do they? They just tell us the monthly payment was $895.10 for 8 years. Anyway, here's how the solution goes. You use the APR loan payoff formula. So how many months have you paid? You've paid 96 months, right? 8 years at 12 months per year. So how many payments do you have left? You have 360, because if it's a 30-year loan, 30 times 12 is 360. Yeah, there's 360 total payments. So if you look at it, you have 264 payments left to make on that loan. And so the formula for this is the loan payoff formula, I think they call it. You take the payment and then multiply by 1 minus 1 plus r over n to the minus nt divided by rn. And when you work that math out, you end up with $106,762.10. This is your homework problem 3 from module 6, okay? If you're wondering. With my numbers, of course. You have different numbers, but same formula will work, okay? Any questions?
Where did you get the 360 from again?
360 is the total number of payments in the loan. So it's a 30-year loan, so 30 times 12 is 360. I don't know if your problems all are 30-year loans or if they've randomized that in the problem set. It looks like everybody's got a 30-year loan in problem 3. I think. I don't know. If I had a color printer, they usually like make red the things that are randomized, but I've got black and white, so I can't tell. By the way, I think this is the same formula we were just using, right? This is just the payment formula, isn't it? Solved for amount instead of payment. It's not really a totally different formula. But the key is, and whatever you put into NT here, right? It should be the number of remaining payments. That's the number that needs to go there. So for this one, it's 264. All right. So that brings us to chapter 12, which is on combinatorics, and at great risk to my... All right, I think I got away with it. So next up, we're talking about combinatorics and probability. All right, so I'm attempting to tell you things about section 12.1 and 12.2 for the rest of today. All right, and so the main idea here is counting principle. All right, so what is the counting principle? Counting principle says this: let E be a multi-stage experiment if n1, n2, nk are the number of possible outcomes at each one of the k stages. All right. Then there are n1 times n2 times nk possible outcomes for E. So let's see here. Let's look at some examples, yeah? So you flip a coin 3 times, right? And I'm assuming this is a 2-sided coin, all right? Like you got heads and you got tails, right? So each coin flip, how many possible outcomes are there? Each coin flip, you've got what? Either heads or tails, right? Each coin toss gives either head or tails, right? So in the language of the counting principle here, I have n1 equals to n2 equals to n3. They're all equal to 2. All right? So how many possible outcomes? 2 times 2 times 2. Yeah? So total number possible outcomes 2 times 2 times 2, also known as 8. Right? Now your textbook discusses a number of different ways to kind of think about this, think through it, right? Like you could make a set that just has symbolically all the different possibilities, right? Like what would the set look like? You could have what? You could have heads, 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 right? You could have heads, 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 tails. I'm getting tired of writing it that way. I'm going to bail on that. Let's try this again. Head, head, head. Head, head, tail. Head, tail, head. Head, tail, tail. Right? And then you could have tail, head, tail. Tail. Oops, I meant to put tail, head, head. Oh well, my bad. Tail, tail, head. And tail, tail, tail. I mean, these should be distinct, right? I mean, is there any repeat here? I think there's 1, 2, 3, 4, 5, 6, 7, 8. So that's kind of kind of a pain to list them out like that, right? Another way you could make a diagram would be like you could draw like a tree diagram with heads and tails going two different directions. Your book has some pictures like that. So I don't know. I don't think we necessarily need this kind of list to do this kind of problem. So let me just not say more about it in that regard. Let's look at another example. So I'm going to try to look at a bunch of examples for you guys here. Let's see here. I'm trying to leave the examples in the textbook for you guys to read. I'm going to try to go work problems in the back of the section instead today, I think that'd be more helpful to everybody. Let's see here. So example 2. Let's see here. It says, this is exercises 1 to 10. List the elements of the sample space defined by each experiment. So here it is. Select an even single digit whole number I'm like, wait a minute. There's infinitely many even numbers. Oh, hold on a second. What did it say? Single digit, right? So what are the even single digit whole numbers? You got what? 0? Well, whole number. Is 0 a whole number? No. I think 0 is not a whole number. So 0 is a whole number? This is not 12.1 number 1. Fortunately, I have, well, that does whole numbers. W does not include 0.
It is a whole number, according to Google.
I don't care about Google. You guys, Google's dead to us. The question is how does the book define W? You said W. What were you looking at? Google. See, Google can't agree with itself either. I got 2 different Google answers. The question is, what does the book define W to be back in the first chapter, which I've left in my office?
It is a whole number according to the book.
It is a whole number. Okay. 0 then. 2, 4, 6, 8. There you go. So if you're going to select an even single digit whole number, you've got what? You got 5 choices, right? So it says list the elements of the sample space defined by each experiment. So this is the sample space, so-called sample space for this experiment would be that. That's it. For this is like 12.1 number 1. All right. So now let me add to this. How many 3-digit numbers where the digits are even, right? So how many 3-digit numbers where the digits are even? So those are your choices for an even. If the digits are even, each digit forming the number has to be taken from that sample space, right? So the way I think about this is I'm forming a 3-digit number, right? So I've got 1, 2, 3 blanks to fill out, yeah? And how many choices do I have for each one of those? It's basically an experiment. I have n1 choices for this one. I have n2 choices for this one. I have n3 choices for that. How many choices are there? Each time I'm picking an even number from my sample space, right? So in this case, n1, n2, and n3, they're all equal to 5. So the total, how many? This gives n1 times n2 times n3, which is 5 times 5 times 5. That's 5 times 25, which is 125. There are 125 possible such numbers. I mean, I think it would be hard to count those directly, wouldn't it? I mean, we could start listing them, right? Here we go. 0, 0, 0, 0, 0, 2, 0, 0, 4, 0, 0, 6, 0, 0, 8. We're going to be here a while, aren't we? 0, 2, 0, 0, 2, 2, 0, 2, 4, 0, 2. No one wants to see this, right? So, and so forth and so on. Very much later, we get to 888, you know? There are 125 of these. I hope you see the power of the counting principle, right? To like just actually count them is a pain, but if we use the counting principle, we can calculate answers to somewhat complicated questions with a minimum of effort, all right? But we have to be careful to understand the question which is asked. That's often the problem. Let's see here. Let me find another one that's actually more interesting. So let's look at example 3. This is going to be number 19, all right? Number 19 from section 12.1. And here the question says, the following experiment. 2-digit numbers are formed. 2-digit numbers with replacement from digits 0 to 9. Now digits 0 to 9, what are those? You got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are your digits from 0 to 9, right? So how big is your sample space for each one of these experiments? Think of the experiment is the picking of the number, the picking of the digit. We're looking at a 2-digit number, so I make myself 2 slots. I need to fill in those slots with 2 numbers, right? The first slot, I pick what? A number from the sample space, right? How many choices are there? 9? Ooh. 1, 2, 3, there are 10. There are 10. Because we include 0, right? So there's 10 choices for this one, and there's also 10 choices for that one, right? In other words, in my previous notation, n1 equals to n2 equals to 10. So n1, n2, the total number is 100. There are 100 such numbers. All right? How would this look different? How would this look different if we see that word with replacement? What does that mean? That means you can have numbers like 11, 22, 33, 44, 55, 66, 77, 88, 99. These are numbers, you're using the same digit twice, right? What if you don't allow that? How many 2-digit numbers without replacement? From digits 0 to 9. In other words, right? In other words, we're looking for a 2-digit number where you're not allowed to have multiples of 11, essentially, right? I mean, well, 0. You can't have 0, 0. You can't have 1, 1. You can't have 2, 2. You can't have 3, 3, right? So forth and so on. So we can think about this as a 2-step experiment, right? You pick the first digit. You pick the second digit. What does n1 equal to? To start with, you have 10 choices, right? You can choose 0, 1, 2, 3, 4, all the way out to 9. So you've got 10 for your first choice. But your second choice what has happened? You've used one of the digits, right? So in your second step, your sample space is shrunk. You only have 9 choices. So you got 9. So 9. So total number, n1, n2. There are 90 such numbers. Can anybody tell me another way to think about that? How does 90 relate to 100? Plus 10. So we're getting rid of 10 choices, aren't we? So we're getting rid of what? 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. Those are 10 numbers like that. So 100 minus 10 is 90 is another way you could think about it. But I think that way of thinking is more complicated. It's much better to do the 9 times 10 idea. Right? Because what if instead of 2-digit numbers you said, how many, well, what if you did how many 3-digit numbers? I can't spell. 3-digit. With replacement. So then you've got 3 things, right? You've got 10 for this one, you've got 10 for that one, you've got 10 for that one, if we're allowing 0, 0, 0 as a number, right? And so that gives us n1, n2 to n3 is 10 times 10 times 10, which is 1,000. How many 3-digit numbers without repeating a digit? Without repeat. You get 10 for the first choice, right? You get 9 for the second choice, and you get 8 for the third choice. Because you can't repeat a digit, right? So you pick one out, you're left with 9. You pick another one out, you're left with 8. So 10 times 9 times 8 would be the number of 3-digit numbers without repeating a decimal, without repeating a digit. And I think somebody told me that was, what was it, 720? Yeah. All right. Let me see if I can find us another example here. I guess that's probably it for the section 12.1 problems. All right, so next up I need to talk to you guys about, if I can find my markers, what's a permutation? So now we're in section 12.2. What's a permutation? So your book says a permutation is an arrangement of objects in a definite order. So the order matters for a permutation. All right? So I think my first example about heads and tails kind of gives you an example of a permutation, right? I was distinguishing between whether you get, heads first and then tails, or, tails then heads then tails. Like the order mattered. I was thinking of those as 8 different cases. If if you didn't care about the order of the flips, if you just counted the total number of heads and total number of tails, that wouldn't be a permutation. Let's see if I have a good example in here. So here's the notation. Our permutation formula is as follows. The number of permutations of n distinct objects selected k at a time is, here's the notation for it, p n comma k, and that's equal to n factorial over n minus k factorial. Of course, I don't need to explain the factorial since you all know what factorial means. I'm joking. So if you want to know how to read n factorial, it's like this. N! Sorry, it's horrible. Let's see here. So the example that your book gives, which is kind of silly, is your, let's see, what example am I on here? 4. Forming a playlist with 3 songs. Now they give us generic things like reggae and rock and was it country? I forgot. We should. What do you want our 3 songs to be? I'll let you guys choose. Song number 1. It's audience participation time. No, I don't want a genre. I want a specific song, like California Girls. Is that from the
Katy Perry.
the Katy Perry? Oh.
It's actually spelled as a U for girls, but it's
Oh boy.
This is a lesser known remake of California Girls. It was spelled properly. Yes, here. Yes. Other options? If it rains, it pours. Thriller?
just since I'm probably
Thriller.
this is
Fun fact, when I was 6 years old, somebody I knew had I think a birthday party it was called Skate Estate, which was the local skating rink. And this was like 1980, I don't know, 5 or something. And they played the music video from Thriller. I was like 6 or something at this time. It was terrifying.
oh yeah, because it has zombies.
I dreamed that Michael Jackson was under my bed. In retrospect, that was a much scarier dream than I realized at the time.
That's funny.
So, this is an example of permutations because if you're making a playlist, right, there's a big difference between whether you play California Girls and then If It Rains It Pours and then Thriller versus you start with Thriller, then you play California Girls, then you play If It Rains It Pours. I mean, there's permutations, right? So the order matters here. And so we do Aw. Oh, I've forgotten here. So we're with 3 songs, but these are chosen from oh man, I messed up the example. We need more songs. From 8 songs. All right, so I need quick. I need 5 more songs.
Highway to hell. Don't stop believing.
Highway to Heaven. Don't Stop Believin'. Landslide. Like that's like, is that Fleetwood Mac? What was that? Staying Alive? I thought disco was dead. What happened? Salsa? Let's see here. 1, 2, 3, 4, 5, 6, 7. We need one more.
Dancing Queen.
Dancing Queen. This is a very, for your generation, this is a very dated list. Like, you don't value your own generation's music? I mean, like, what's happening here? Most of it's trash. I do have a friend who refuses to listen to anything until it's been out for at least 10 years as a means of filtering out garbage. It's pretty right. So if we're going to form a playlist with 3 songs chosen from the 8 songs, that's the context here. So the number of such playlists is P of 8, 3. So we have to calculate 8 factorial divided by, you're like, what is 8 factorial? I know, I'm getting to it. 8 minus 3 factorial. All right, so time for me to explain what factorial means. So 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Of course, you don't really have to put the multiplied by 1, right? I'm just putting it there. 8 minus 3 factorial is 5 factorial. What is 5 factorial? That is 5 times 4 times 3 times 2 times 1. So this is what factorial means, all right? I'll do some more factorials next page. Let me just focus on this example here for a moment. And so you see what cancels? So you can cancel the 5, cancel the 4, cancel the 3, cancel the 2. Of course, the 1s don't even need to be written technically. And you just get 8 times 7 times 6, which is what? Get my calculator out here. What do you got? 336. Yep. So there's 300 so you can form 336 possible playlists if you pick 3 songs to make a playlist from. If you have this roster of 8 songs. All right. Let me talk more about the factorial since I kind of owe it to you. Factorial is it's an interesting function. So the way this works, n factorial is equal to n times n minus 1 times n minus 2 dot 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 3 times 2. And I like to throw in the 1 just for good measure. But you can define it recursively like this. Really, n factorial is equal to n times n minus 1 factorial. So like you can always build the next factorial from multiplying the last one by the next number. That's how it works. There's more to it, though, that's not at all obvious, I think, which is that by definition, 0 factorial is 1. And 1 factorial is 1. All right. Once you know that, you can build 2 factorial. See, 2 factorial is equal to 2 times 1 factorial by the recursive rule, which is 2 times 1. So 2 factorial is 2. 3 factorial is 3 times 2 factorial, which is also 3 times 2, which is 6. 4 factorial is 4 times 3 factorial, which, by the way, is 4 times 6, which is 24. 5 factorial is 5 times 4 factorial. Incidentally, is 5 times 24, 120. This is relaxing. 6 factorial is 6 times 5 factorial, which is 6 times 120, which is 720. 7 factorial is 7 times factorial, is 7 times 720, which is 1040, I think. Factorial is 8 to 7 factorial, which is equal to, all right, I need a calculator. 40,320. So factorial is really kind of weird, right? I mean, it's not like other math that we do in other courses that much, right? It's like it's quite removed from other things. But this is These kind of patterns are very important to math, science, and engineering, and especially counting, because we'll see that the factorials come up in all of the formulas for counting here, permutations, and what we'll soon talk about, combinations. All right. Yeah.
In the example before,
Mm-hmm.
where you had the 8 factorial, and you went from 8, all the way up.
Yeah.
Just for my curiosity, why wouldn't that be like the example that you gave on the next page, where you're doing like 8 factorial and then equals 8 times 7 factorial, and then coming up with that big number? Like, how do you know when it's asking for which?
How do I know when it's asking for?
So like on
Oh, the next. Oh, okay. So the next page, I was just illustrating like what the factorials are. Another way you could do this calculation would be this. You could have said that this is equal to 8 times 7 times 6 times 5 factorial divided by 5 factorial. Just cancel the 5 factorials and get the same number. Like, that's another way you could do that calculation. I just think for students who are starting and who don't, want to be too mathematically sophisticated, just multiplying, like writing the numbers out like this, it doesn't take a lot of work, and it's hard to get it wrong, like this way of doing it, but you can look at it as 8 times 7 times 6 times 5 factorial, and then the 5 factorials cancel. I mean, there are other ways to process that calculation. Hey, let's look at something here for a second before I forget. So, do you guys have calculators handy? If you do have a calculator handy, try calculating 12 factorial. See what you get. What happens? Get a really big number? It's pretty big, right? So 12 factorial is, so you can still do it, right? It's what? It's about 47 million. What happens when we get to 20 factorial?
Oh my.
20 factorial is 2 quintillion, apparently. Thank you, Wolfram Alpha. I didn't know the name for this, but there it is. 2 quintillion. What if you do 100 factorial? How big is that? I think your calculator probably balked at that, right?
50.
There you go. It's about 9.33 times 10 to the 157 power. That's big, even in terms of like national budgets, So factorial, if you want a function which gets big faster than anything else, it's hard to beat the factorial. Factorial is like one of the quickest growing functions that we know. All right, it's just huge. All right. So let's look at. Oops, I got back. Nope, wrong button. There we go. Come on, you can do it. Okay. Okay, so I would say in terms of things to put on your formula sheet for next time, maybe the factorials out to 10 wouldn't be a bad thing to have on hand, I don't know. It might be useful. Of course, you can just calculate them also. Really? Moving on. What if instead of picking 3 songs, we had picked an example, the last example I did. What if instead of picking 3 songs, so example 4 continued, if you pick 5-song playlist, right? From 8 songs. then what do you have? You need p of 8 comma 5, and that would be 8 factorial divided by 8 minus 5 factorial, right? And what would that be? This, now you've got, really?
It worked.
All right. I should have a ceremonial destruction of this if I stop using it in this class, because if I stop using it in this class, it's dead forever. So we should just take several minutes to just destroy it. I'll bring in a sledgehammer, you know, something like that. So 8 times 7 times 6 times 5 times 4 times 3 times 2. And this is what? 8 minus 5 is 3 factorial. So you've got 3 times 2, right? 3 factorial. So we can cancel the 3, cancel the 2, and we're left with what? 8 times 7 times 6 times 5 times 4, whatever that is.
6,720.
So 6,720. So there's a lot more playlists that you can form if you're picking 5 songs, right? But keep in mind here, we're saying that the order of the songs matters, right? Like the playlist which plays Thriller first and plays, I've lost my songs, California Girls second, is different than the playlist which plays California Girls first and then plays Thriller second, right? So the order matters. That's why we're using permutation to count the number of playlists, all right? Let's move on here. So next up, we can talk about, excuse me, the number of permutations of objects, some of which are identical. So let me write this down here. Permutations of objects, some of which are identical. So I guess to be clear, in my previous example, I wasn't allowing us to have a thriller playlist, right? I can't just pick Thriller 5 times in a row as my playlist. It's forbidden, right? So I was assuming that our objects that we're picking are distinguishable, right? 5 different songs for the playlist. Now this here is addressing the question, what if you allow a repeat? What if you allow a repeat in your playlist, you know? So here it is, the number of distinguishable, if I can spell distinguishable, permutations of n objects of r different types where K1 identical objects of one type and then you have K2 of another, and so on, is n factorial divided by K1 factorial times K2 factorial KR factorial. All right, where K1 plus K2 plus plus KR is equal to n. So let's try to put this into place for playlists, all right? Let's just apply this idea to playlists. How are we going to do this? So let's you have n objects of r different types, right? So let's suppose that we're going to, pick 3 songs from our 8-song list. But 2 songs repeated. So let's see here. So basically, how many different types of songs are we then? We've got K1. Let's say K1 is the one repeated, right? And then we've got K2, which is what? Which is 1. So I'm saying 3 total songs. 1 of them's repeated, right? So I'm picking the same song twice. So there's 2 of those, and there's 1 of the other. And so the number of permutations in this sense would be what? 3 factorial. Wait a minute. Excuse me, what's n? My bad. N is what? 8. So 8 factorial divided by what? Yeah, 2 factorial. 1 factorial. It seems wrong to me, but this cannot be right. It seems way too big to me. Maybe I'm just not seeing it. Let's try this out. So what do we got? 8 times 7 times 6 times 5, 4 times 3 times 2, right? Divided by 2. Wow, that's a lot, isn't it? Oops, the 2's cancel, right? Are there really that many? I just don't believe it. Let's try the counting principle to solve this problem. Yeah? Oh, maybe I'll see it from this. I don't know. So the counting principle says there are 3. We're picking 3 songs, right? The first song. So let's say the first song is the one which is not repeated. I have to make a diagram. So it's like you have A and then B and then B, or you have B, A, B, or you have B, B, A. Those are either you're gonna, if you're picking 3 songs with 2 songs repeated, either you've got the repeat at the end of the playlist, or you've got the repeat at the start and the end of the playlist, or you've got the repeat at the start of the playlist. But some way or another, you're going to repeat that song twice, right? So this first case, how many choices do you have? How many choices do you have for A? Well, there are 8 songs, right? So you've got 8. How many choices do you have for B? You have what? 7 choices, right? So I have 56. I have 56 possible choices like that. Of the BAB pattern, I have how many choices for B? I've got 8. How many choices for A? I got 7. It seems to me that this should be each time I've got 8 choices for B, I got 7 choices for A. So if I'm counting things correctly here, we should have 56 plus 56 plus 56 choices, which would be 100 and what? 168.